Okay, welcome back. We're going to start chapter 9 today, and we're going to talk about comparing more than two means. I think we can see the natural progression in chapter uh, 6. In chapter 6, we compare two means. In chapter 9, okay, chapter 5, we compare two proportions. Chapter 8, we compare more than two proportions. Chapter 6, we compare two means. Now, chapter 9, we compare more than two. So, this is a generalization of what we've already seen before. So we are going to motivate this by and also have your computer ready because you're going to boot the movie again. So you should follow along with me. The earnings by degree data set. Now, where is that? So that's found in, if you go to our Moodle page, there's a data sets tab that's always there. So go look for the sheet, the tab that says, do you see salary? This one. So look for the salary tab. You should see this. Earnings in thousands of dollars. This is your annual salary and degree. What is the highest qualification that you have? So I would strongly encourage you to follow what I do. So fire up your Jamovi. I'm going to do that myself. Okay, so here's my Jamovi. And when you copy things, don't copy the title. Okay, don't copy the cell names which have the variable names. Just ignore that. It's quite a large data set, this one. So yeah, so it's, I think, okay. All right. So copy this. So just copy this. Then in Jamovi, as usual, you just paste. Now, sometimes Jamovi is smart enough that it recognizes that something is quantitative. Did you see that A has a ruler there already? Do you see that icon there for the ruler? Now, what does the ruler mean? It means it's continuous. That's correct. And do you see that for B, it's those circles, categories? That's correct. So this is categorical. This one is quantitative. So you don't have to change the status. You can change the name though. I recommend that. So if you change the name, this one was what, earnings? I would encourage you to always use one word. All right. If you must use two words, then put an underscore. So I would say earnings in thousands or something like that. Okay. Okay. There's no need to change the measure type because the measure type is already correct. It recognizes that these are numbers, so that's good. So don't touch that. Right. Then for B, in fact, let's take a look at, you see, they even helpfully tell you the levels. What are the levels in B? Some, associates, bachelor's, master's. So I'll explain. So this just categorizes people based on their highest qualification. Do you have a doctorate? Do you have a master's, bachelor? So nothing much not to understand. Some means they didn't complete the associates. Associates degrees are 2 years. So this is less than 2 years of college. That's what some, right? Okay. So we have this. This one, we can rename this to be quals or something like that. Okay, highest qualification. There's no need to change the measure type. It is by default correct. Okay, so since we are on this page, uh, we'll do a few more things. I'm going to show you draw, how to get some statistics first. All right. So just follow what I do. And by the way, if you don't catch everything I do today, there's a YouTube video which I put a link to on our Moodle page. You can always go check it out. Right? Look for I do teach all these things in the YouTube video, so you can check it out anytime. It's not that hard. So if you want to get statistics, what you do is you go to exploration. Do you see exploration? Descriptives, like that. Okay. So here's a few things to do. First of all, um, I'm trying to use a new strategy here. Let's go with earnings in thousands. Go to variables, press this arrow like that. Did you see that? Do you see that something happens when you do this? First of all, let me ask you a question. What do you think N243 means? Anyone have any guesses? What do you think 243 is? Like, what are they telling you? The number of observations. Good. The total number of observations in the data. That's an important number. You might want to copy that onto your slides. All right. Anyone have any guesses? What do you think mean 58.15 is? What does this number mean? Can someone tell me? What is 58? First of all, it's in thousands, okay? What is 58.15? It's some kind of average. What average is it finding? We know there's 243 people. So this mean is the average what? The earnings, that's right, salary. It is the average salary in the entire data set. Copy this number down. This, by the way, is also known as the grand mean, just so you know. I mean, they don't write the word grand here. Grand mean because it is the mean across everybody, okay? So copy this number down. The grand mean is 58.1K dollars a year, all right? That's the average grand mean salary for everybody in the data set. Okay, so that's easy enough. Here's a small thing that you can learn as well. But don't we want to know what the statistics are for each of the qualifications? To do that, there's one additional thing. You see, while highest qualification, you go to split by. This puts them into buckets. Split them according to their qualifications. That's why it's called split by. One thing I like about Jamovi is they use very intuitive words to describe. Did you see what I did? So just hit that variable and bring it into split by, like what I've done. And did you see they did exactly that? So can anyone tell me how many people in the data set had a bachelor's degree? Anyone? Just tell me a number. 46? Did you see that? This gives you the bucket sample sizes. It's very useful. All right. I'll explain what missing means. Missing just means that there were no people who declared their degree but didn't tell you their salary. In other words, if I have associates 1, it means there was someone in the data set that told me they have an associate's degree but refused to tell me the salary. Did you understand that? But there are no cases like that. This is a simple data set. There are no missing values. So Jamovi is very flexible. In other words, it doesn't mind if in the data set, for some reason, I mean, when you do your analysis, you may actually have a situation where some people didn't answer your questionnaire fully. That could happen. Jamovi can handle that. So in other words, it doesn't mind. You have incomplete information. Maybe you didn't have salary information for someone. So that's fine. Okay, but that didn't happen here. Anyone want to tell me what is the mean salary of master's degree holders in this data set? Anyone? Do you see it? What is the average salary of master's degree holders in this data set? 71.8K. You can see that there. So very, very intuitive. What is the standard deviation of the earnings of people who have some college degree, some college experience? Can you give me the SD? 23.79K. That's right. So very broad, very, very high. The standard deviation is very, very high. Right? There's a lot of variability, basically, which we can understand. Okay, great. So that's how you get these. So don't forget the split by. And then how do you see histograms? That's even easier. Go to plots. Do you see histogram? Let's click histogram. It is smart enough to draw exactly what you want. Did you see that? One thing I really love Jamovi histograms. The colors that they pick are somehow very appealing. I don't know whether you realize that. It's nicer than Google Sheets. It's a bit more, it's a little bit not so harsh. It's really nice. The histograms really are very, very good. So that's how you make it, the histogram. See, these are histograms by groups. doctorate holders, masters. It's pretty simple. There's nothing very much to explain here. You get the separate histograms by buckets. If you wanted to draw a histogram of all the data, what do you think you should do? Go to this thing and remove it. Don't split the data. When you do that, did you see the histogram change? You don't put them into buckets anymore. This is an overall salary histogram for everybody. If you wanted the salary by groups, you split them by groups and the histogram adjusts accordingly. See, Strategy Movie is a very wonderful tool. You can continue to use it even after you finish this class. Okay, very nice. So, okay, so that's plotting. So let's go back to our slides. I'm going to leave this here because we're going to need this in a minute. All right. Don't forget the grand mean, 58.8. We're going to get that later. All right. The grand mean. Remember the grand mean? I'll put this back. If you see the, oh, what happened? Okay. No, don't do that. Okay, write this down. The grand mean is 58.16. Okay, remember that. And we're going to need that later. Okay. So let's go back to our slides. Consider the earnings by data set, earnings by degree data set. Two variables are measured. Of course, highest qualification is the first one, and annual earnings. Okay, so we measure the highest qualification of the person and the annual earnings. Can I ask this question? What do you think is the most reasonable choice as the explanatory? How should we put them into buckets? According to which variable? Anyone? What's the most natural thing to split them up by? Highest qualification. That's what we just did. It doesn't make sense to split them by salary because the salary is quantitative. So I would say this is the one. Is this categorical? Obviously, yes. Highest qualification was categorical. Therefore, the response has to be the annual earnings. And I hope you realize the annual earnings are definitely quantitative. Let me ask you a question. Can annual earnings be categorical? Yes, it depends how you ask the question. If you ask people, tell me your annual salary, then that makes it quantitative. But I don't know whether you've done any questionnaires like this before. Annual salary is not asked in a quantitative way, but they ask you in a range. Did you see that before? Anyone have any idea of why asking your salary as a categorical sequence of ranges may have some advantages? Anyone? What do you think is the advantage of asking people their salary in a sequence of ranges categorical like that? Anyone have any idea why? Why would you do that? As opposed to asking people, tell me your salary in a quantitative way like that. Anyone have any ideas why that might be something you might want to do? Anyone? Any ideas why? That's right. Sometimes people might not know, or sometimes they might not want to tell you because they feel that this is a privacy issue. People are more comfortable divulging information. Maybe they can hide behind the category so it doesn't feel so invasive or something like that. So these are things to think about. But in this data set, it's not like that. It's quantitative, okay? So write down the values of n sum, n SOC, and all the, okay, so I'm quite sure you know what these mean. N SOC means how many people have an associate's degree. S sum is the standard deviation of the salaries of people who have some college like that. So you don't have to write them all down. There's a lot of numbers. Make sure you have produced this for yourself and just write down a few. Right? Just write down a few just to show yourself that you know where these come from. So n sum would be 50. X bar bachelor's is 56.08. You know, you get the idea. So you can just write down a few of these things. These are all the observed statistics. You get them directly from the movie. Okay. Compute S pooled. Wow. Okay. We are not going to ask you to compute this in class. There's no time because it is quite tedious. And there is no way, surprisingly, to get this on Jamovi. You actually have to do this by hand. Still, I mean, with a calculator. But don't freak out. This formula looks pretty bad, but it's not. I'll tell you why. If your eyes are sharp, you will realize that this S pool definition is an extension of what you've already seen when you compare two groups. I'll tell you why. If I pretended that all these groups did not exist, it stopped here. The formula stopped here. Is this something you have seen before? Sample size less 1 times standard deviation square of one group plus sample size less 1 standard deviation square of another group. And then stop there first, right? Two groups. Then don't you have the end of the first group plus the end of the second group? But can anyone tell me, what did we subtract with last time when we were comparing two means? 2. So why are we subtracting 5 now? Because we're comparing 5 groups. Did you see that? So the only thing that's different here is the arithmetic, not even the math. The arithmetic gets a little bit more involved because it's just small groups to think about. All right? Always learn things this way in math. When it was 2 groups, it was much easier. This and then this plus this, less 2. But now that 5 groups, you extend in the same way to all the groups. So I will give you the answer. Okay, I'll just show you. Where do all these numbers come from? All these numbers come from Jamovi. The N, the S, and all that. So the N's come from, well, here the N's. The N's are all here. The S values are all here. Standard deviations like that. So it is a slow process to slowly process these things, but it can be done. The answer turns out to be 33.93. So write that down. We're going to need that. The answer is 33.93. I'm going to show you why this number makes sense. Remember the rule I told you that when you find S pool, your one way to check whether what you have done is correct is to see whether your S pool value lies within the smallest S and the largest S. Do you remember that? Your S pool cannot fly outside the smaller S and it cannot be bigger than the larger S. Now that there's 5 values of S, that same rule applies. So let's go back to Jamovi and have a look. See, look at the values of S here. We have 20.7, 39.3, 33.3, 44.1, 35.4. Do you see that? So the smallest value of S here turns out to be 20.79. The largest value of S turns out to be 44.15. So is 33 something reasonable? Is it sandwiched between the smallest and the largest? Answer is yes. That's how you know your answer is correct. If you get an S value of like 105, that's out because that's bigger than the largest. Or if you get an S value of like 4, that's smaller than everybody, so that doesn't work as well. So we have all that. All right. So we have our values of S here to help us. And so we have all the other numbers here like that. Okay, so we are going to leave this for a while. What's the definition of mu associates? Every time you see a Greek letter, what are the first words you should say? Mu associates is a. Every parameter definition must start with these words. Long run. What is mu? Mean. The long run mean every time you have the word mean, you need to have another word after that for the quantity. The long run mean what? What is the mean about? The long run mean? This is quite important. Okay? There's always a little bit of hesitation. Long run mean, what is the quantity that we are finding a mean for all this while? Does anyone know the answer? Long run mean? Salary, good. The long run, yeah, not long run mean associate. That means nothing. You don't say long run mean associates. What does that even mean? The long run mean salary of people who have an, yes, good. So it's something like that. So mu associates is the long run mean annual salary or earnings or whatever of people whose highest qualification is an associate degree. Stuff like that. So I hope these things are coming more naturally to you by now because they are just more of the same. This is exactly a generalization of what you've done for two groups. Now there's just five groups, that's all. But the other definitions still stay the same. Right? Long run mean annual earnings of individuals with highest qualification is an associate's degree. Something like that. Okay. What would be a reasonable way to see how different all these five means are? We've talked about this. One possibility is to use the maximum mean minus the minimum mean. Do you agree? One way to compare five groups is let's find the group with the highest mean salary and let's find the group with the smallest average salary and find the difference. We have also discussed this when we talked about proportions. Can anyone tell me what disadvantage does this have? We have discussed this before. Anyone know the answer to this question? Why do I not like this? It's not wrong, but why is this not so good? Yes.
You don't use the rest of the data.
That's right. And I told you there's a sin, remember? In statistics, there's a statistical sin. You don't leave out data. When you do max minus min like that, you have five groups. You are essentially throwing away data from three groups. That's not good. So that's why we don't like this. Good. All right, that's correct. We are not using all the observed data in the best possible way. I want to stress, it's not wrong. It's not wrong, but it is less good doing it this way. Right? It's not wrong, but you are not using your data in the best possible way. Okay. So the uh, the other thing that we want to do is going to be using a statistic that is better than that. But we'll come to that. So let me ask you this question. What do you think the null hypothesis is going to look like? Anyone? Based on everything that you've learned so far from me, they are involving mu. Can you tell me, can anyone tell me what they think the null hypothesis looks like? First of all, how many mu's are there to compare? Five. So what do you think the null sounds like? Mu sum equals, yes, good. So the null says mu sum equals mu associate equals mu bachelor equals mu master equals mu whatever. Okay. The alternative looks the same. Not all mu's are the same. Again, there are many ways for them to not all be the same. Maybe two of them are the same, three of them are different. So there's other things you can do as well. Okay. So in words count. Now, can someone give me the language of what the null is saying using non-statistical language, using the words association? Anyone want to try? What is the null saying? There is, if you want to use the word association, I've taught all these things in the proportion problem. There is no association between salary and there is no association between salary and qualification. That's right. Something like that. What do you think the alternative says? There is one. Good. I don't know whether you realize by now that the way I make my notes is actually to help you study. There's a high degree of similarity between chapter 9 and chapter 8. It's just that in chapter 8 it was proportions, now it is. But a lot of the same ideas are circulating around and around again. Okay. Now, I'm going to ask you this question. It's a bit of a I would say it is a very important statistics question. If the null is true, let me show you the null. If the null is true, are we justified in computing x bar? Now, note this, first of all. I think all of you know what x bar is. Right? It's some kind of mean, right? The fact that there is no subscript here, the fact that there is no subscript here means what? That this is the grand mean. Now, I did ask you guys to copy down the grand mean. Did anyone do that? What is the grand mean for this data set? 58 point something. That's right. Good. That's the grand mean. Now, my question to you is this. If the null is true, if in the long run, all the groups in the long run on average earn the same, are we justified in computing the grand mean? Do you think the answer is yes or no? Good. The answer is yes. Why? Because it's not. Yes. So one thing I'm going to say is this, all right? I told you I don't want, I hope, none of you 10 years down the road, if someone asks, did you take statistics in college? Yes, I did. What was it? Oh, I don't know. It was a bunch of formulas there behind the lines. Because I try to make my statistics class different from other professors because I try to tell you the reason why you do things. It is much easier to teach a statistics course where I say, here's a bunch of 25 formulas, go use them all. Don't tell you why. I'm trying to teach you beyond that. Something as simple as a mean, it's easy to compute a mean. It's easy to report a mean, but what I'm trying to tell you is, are you justified in reporting that number? Are you justified in reporting that number? The point I'm trying to make is this. I'm trying to make this class be beyond just showing you a bunch of formulas. Because too many statistics classes are like that, and the only takeaway people have at the end is, I don't know. Oh, I don't know. It was very boring. It was just formulas all the time. Yes, there are formulas in statistics. It wouldn't be a statistics class if there were no formulas and no numbers. But you must understand what you're doing. And the point is, I'm trying to tell you, if the null is true, only then you should ever report a combined mean. It makes no sense to lump everybody together and give a mean if the means were different. Now, can you get an answer for this? Of course. Anyone can compute a mean, but should you be reporting it? That's very important. We live in an age where people have lots of misinformation everywhere. It is very important to understand what you're doing. It is very misleading to report this if the null was not true. So you got the answer right. If the null were true, you are justified in computing x bar. And so what is x bar? Of course, you got that answer right as well. So let me ask you another question. If the null is true, is this sum, you know what a sigma sign means, it's a sum. Is this sum over all groups going to be small or big if the null is true? What does the null say? The null says all the groups are basically the same when it comes to the mean. If the null were true, would this number, what does it mean? Take one group's mean minus the grand mean. So you're finding the difference between that group and everyone. Square that difference and then go to another group like that. We're not going to ask you to do this thing by hand. I just want you to imagine what you're doing. If I take each group one by one, take that group's mean salary and subtract the one that's the grand mean for everybody. Now, if the null were true and there was no difference, would this number be small or big? Very good, small. If the null were not true, would this number be small or big? Really keep that in mind. So if the null is true, this number is small. Again, I'm going out of my way to tell you why. Why am I fixating on this? It's because the statistic I'm going to introduce to you today has this number in it. Okay. Do you remember that when I taught you for proportions, what was the name of that statistic I introduced to you to quantify how different groups are in terms of their proportions? What was it called? Chi-square. Good. This is the analog to the chi-square. The statistic I'm going to introduce to you is called Snedeker's F. Snedeker is a person's name. And I'm going to get to that in a minute. But let me introduce the statistic first. Snedeker's F statistic looks pretty bad, but we are not going to ever ask you to calculate this by hand. I want to focus on something. Do you see that Snedeker's F statistic has this quantity sitting on top? It has a slight difference. There's an NI here. What does that mean? Does a group, yeah, that's sample size of the group. If a group has a large size and has a mean that is very different from everyone else, will it make your F statistic go up? Will a large group with a very different mean make your F statistic? Yes. Therefore, if your F statistic value is big, should you reject the null? Yes, because the null says all the means are the same. If you are getting a large F, what does it mean? It means there's a group out there that either is very big or has a mean that is very far away. And the other thing to note, do groups that have larger sizes have more say in the F statistic? Yes, this is again a House of Representatives kind of idea. California has 50 million residents. It has way more representatives in the House than a state like Wyoming, for example. Their N is bigger. Senate has a different calculation. Every state in this country gets 2 senators, whether you have a state of 1 person or 10 million people, it's still 2 senators. But I'm talking about the House. This is a House of Representatives kind of argument. A state with a larger population gets more say in the House. A group that has a larger sample size will get more say in the F statistic. Therefore, it has more pull. If you have a larger mean from everyone else, very different mean, and your sample size is big, you're going to blow up your F statistic. So your F statistic increases, you should reject it now for a large F statistic. Now, here's the good news. You are not going to ever use an F table because F tables are difficult to use. We will always have it from Jamovi. I'm also not going to ask you to compute this number by hand. All right. So large values of the F statistic lead you to reject the null hypothesis of no association between the groups. So I'm going to talk a little bit about Snedeker. If you Googled Snedeker Hall, okay, why am I sure? Okay, this is a little bit of flexing on my part, little bit, because Snedeker Hall is home to the statistics department at Iowa State, which is where I did my PhD. Why am I showing you this? This statistic was derived. The word is derived by George Snedeker, who was part of the faculty, not when I was there, he was sometime before me. But basically, in other words, this F statistic was discovered in my school, basically. This was a major flex when I was teaching in Iowa State at that time, because when you come to teach this, you say, hey, guess what? This statistic I'm showing you was actually discovered. It's less of a flex now because I'm not there anymore, but I'm from there. I got my PhD there, so I'm going to flex anyway. So, okay, but this is really, and that makes it what? This is not a very old statistic. It's only about, I think, 80 years old, 70 years old. So when you come to college, Usually the math that you learn in first year of college is thousands of years old. But as you go up in your time here at home, by the time you reach your senior year, if you do any math at all, you are learning newer math as you progress. See, you're learning a formula that's only 80 years old. 100 years ago, no one knew about the F statistic, believe it or not. This is very exciting. I don't know whether you realize. I know 80 years is a long time, but math is thousands of years old, So this is quite a recent thing. Also, this test is called the ANOVA test, analysis of variance. It is the second most famous test in statistics. Does anyone remember the first most famous test? The two sample, what's the name? Yes, good. I told you never forget this. The two sample t-test for comparing two means is the most famous. The ANOVA test for multiple means is the second most famous. Really, the ANOVA test. So if you hear people say, go perform an ANOVA test, don't say, I don't know what that is. This is it. Okay? So enough about this. I'm going to show you where this lives on Jamovi. If you want to get the ANOVA test, follow what I do. Do you see an ANOVA word here? Click it. ANOVA, ANOVA again. ANOVA, ANOVA. When you do this, a table appear. This table. Okay, so you have to tell the computer which ANOVA you want to do. Do you see dependent variable? You click on earnings in thousands. Make sure that you make this the dependent variable like that. Then you need to tell it what the fixed factors are. That's where quals goes. So you have to concentrate like that. That's it. When you do that, did a table appear for you? It should. Can anyone report to me what the F statistic value is? 26.6. Good. That's the one. What's the p-value? Less than 0.001. So do you reject the null hypothesis? Yes. P-value is very small. You will need to know how to read this table on the exam. I'm never going to ask you to compute the F statistic by hand. Okay, but you do need to understand. I also did promise. Is anyone here from the nursing department by any chance? Yes. So we made a promise as a department to the nursing department that we would always teach students to be very careful with the table and to know where the degree of freedom comes from. So I'm going to fulfill that promise now. Do you see a 4 here? Why? Again, how many groups are we comparing? 5 groups, 5 less 1. Again with the less 1. So this one is a 4 here. I promised them that I would tell you that. So the degree of freedom here is always 1 less than the number of groups you're comparing. It's just a small factoid, all right? So with that, let's go back to our slides. We consult Jamovi and we find that the F statistic was about 26.7 and the p-value is pretty small. So on exams, if I don't give you a range, just declare it as a 0. If ever you get something so small and it's not asking for a range, I think there are some homework problems which don't ask for a range, just declare 0 for computer purposes. Right? Okay, we are going to talk next about validity conditions. Does anyone know what they think these sound like? Anyone? You need to have at least 20 observations in each group. Good. That's one. What's another one? Not good. Again, don't say success. No one did. No one said success and failure, which is good, because this is not a. That's right. This is not a proportion problem. So I'm going to throw a curveball. I think that's the expression used. Or something come out of outfield or left field, or out of left field. That's right. I get to get all the baseball. Okay. So there are 3. Okay. There are 3 VCs. You have told me 2 of them. At least 20 observations in all groups. That's the same. All the data should not be too skewed. And I hope you realize that you can check this by looking at Jamovi again. If you go to, I'll come back to this slide. You look at Jamovi, do you see that all the statistics tell you, see the groups 50, 47, 46, everyone's more than 20. But do you think the skewness thing is obeyed? For some groups, but are there groups that are pretty skewed? Are you disturbed about some groups? I would say the sum group and the associates group are pretty skewed. The rest are okay. See, the sum group has a huge peak at the beginning. That's very skewed. All right. So let's drop this for a bit. I'm going to introduce the third VC. This one I'm not going to ask you to guess. All right. It's something to do with standard deviations. The largest SD of any group shouldn't exceed twice the smallest SD of all the groups. Does it make sense what that means?
Yes.
So you check all your SD values, as long as they're all within a range of twice the smallest one, then you're fine. I'm going to check this with you in a minute. All right. The largest SD among the groups shouldn't exceed twice the smallest SD. Okay. So what does that look like? Well, let's see Jamovi now. Look at all the SDs. See, the smallest SD was 20. The sum group had the smallest SD of 20. The master's group has an SD of 44. So do we meet this VC in this data set, anyone? Yes or no? No, we don't. 44 is more than twice of 20. Good. So we have broken that VC actually. So it's not very it's kind of sad. I just introduced the VC and here I am breaking it. Okay. So I am not fulfilling the SD version of the VC. And I also broke the skewness one because one of the groups or two of the groups have quite a skewed distribution. So here's a dirty little secret. Okay. Actually, the most important VC is sample size. If you have this, sometimes you can be forgiven the others. But don't tell anyone I told you this, okay? That will be our little secret. Right? You can have some VCs broken if your sample sizes are large. This one is very, very important. That's why it's always stated first. If you have groups of size 5 or 3, please go home. Right? Don't do anything. You have so broken the VC. But if you have large enough sample sizes, you can be forgiven some skewness. You can be forgiven this SD thing. It's very important. All right, just so you know. Ideally, yes, you should follow all three, but sometimes it's hard to get it. Okay, so we find that the p-value was really small, so we rejected the null hypothesis. What does this mean? The null says that all the means are the same. The fact that you reject the null means you're saying, no, they're not all the same. And if you learn anything from the comparing multiple proportions chapter, what's the next thing we proceed to do? You have rejected the hypothesis that says that all the means are the same. What's the next thing to do? You see which groups are different. Yes, so you do a sequence of follow-up differences between pairs of the data. So it means not all the means are the same. You form a sequence of pairs of differences between the means. Let me ask you a question. You are comparing 5 groups of people in terms of their qualification. How many pairs can you form? Actually, I've asked you this question when it came to the towels and the messages people see on the top. If you have 5 groups to compare, how many ways can you pair up 5 groups? Do you remember the answer or you can quickly compute it now? How many pairs are there to form? Very good, that was fast. 10. You can go back and try. A, B, A, C, A, D, A, E, B, C, B, D, B, E, C, D, C, E, D, E. 10. There are 10 ways to form pairs from 5 groups. Of course, I'm not going to ask you to do all 10. We will do one difference. We're going to compute one just to show you how it's done. Now, the formula for finding the PI for a difference should really not come as a surprise. Have you seen this before? Remember when we compared 2 groups, one mean minus another mean, some multiplier, we'll get to that, S pooled square root 1 over n plus 1 over n. If you have been doing your homework, which I know this class does your homework, you should have seen this formula so many times when I had you practice things like that. Why do I give you homework? So that these things come more naturally to you. This is the same thing as a CI for comparing two means. There is one thing I want to point out. Notice that the S pool here is our old S pool from when I told you to copy down the answer. Who recorded what S pool was? Can you tell me what it was? 30 something. What was it? Thank you. 33 point. Yes, that's right. Now that number is an S pool that was computed over how many groups? How many groups were involved in the computation of that 33 S pool thing? 5. So what I'm saying here is this. Even though you are comparing two groups here, you used an S pool that was derived from 5 groups. Does this sit well with you? Because there are some professors who have actually, well, they didn't fight with me, but they disagreed with me. They said, since I'm comparing only A and B, I should derive an S pool that's only based off information from A to B. I disagree. You know why? S pool is an overall variability measure. The 5 groups are there. Why are we discounting that information? Don't throw information away. You should use an S pool based off all groups, even though you are comparing only 2 groups. Does this make sense to you? Let me give it to you in a more, I guess, an easier way to understand. Some of us, not everyone, some of us have the misfortune of, I don't know whether it's considered a misfortune, but some of us have many breakups before we find the one. Agree? Some people don't. Some people, they find the one when they're in high school and that's the one. But some of us go through many breakups like that. I'm not saying it's good or bad, but that's just the way it is. When you enter a new relationship, do you have some kind of memory warp thing where you have no baggage from your previous relationship? Is it possible? Is it humanly possible to enter into a new relationship and all the things from your previous relationship are not there? That's not the case. We retain stuff from everything we learn in life, good or bad. That's exactly what's going on here. When you calculate S pool, you use the information from every group that you have, even though you are now interested in only A versus B. So I'm trying to give it to you from a relationship point of view because that is quite related. We understand that as you go on in life, you pick up more experience. You can't erase the experience that you already have. You carry it with you. Sometimes that causes problems in the new relationship because of the baggage that we have. That's exactly what's going on here with S pool. S pool pulls information from every group, even though I'm only comparing A and B. Does that make sense? So let's do this together. Oh, let me ask. If you find that a CI for a difference doesn't cover 0, what does this mean? Whenever a CI for a difference does not cover 0, it means that the two means are significantly very good, different. Same. All these arguments are the same. When a CI for a difference does not cover 0, then those means are significantly different. Make sense? Very good. So we are going to practice doing this once. How many pairs can be formed here? Obviously 10, you told me. We are going to do just one. We are going to do a doctorate versus master's comparison. So I'm going to call out our scratch pad. And this is section 11. Okay, here it is. Okay. Let's form a CI for difference in mean for doctorate versus masters. I'll start you off. Remember when you do a CI for difference, it's something minus something. Okay, can I have you start filling numbers in? You don't have to give me generic, just give me numbers to help you out. I will show you my Jamovi page so that you can get the numbers that you need from here. Okay, I want to see if you know what numbers go where. We are trying to form a doctorate versus master's confidence interval. Can someone start it off on Sketchpad? Something minus something plus minus S pool, and you can stuff in your S pool value, which I asked you to copy down in the slides previously. All right. That's right. 87.9. Why? Uh, oh, I think no, it should not be 87. Sorry, it's oh, I think okay. That's actually a good time to point this out. When you look at these things, there's a lot of statistics. Be very careful. What should you be looking at? The mean, not the median. Yeah, but thank you. Right. So you should be looking at means because this is a mean comparison. Okay. So not 87.9. Did you get the right number? You should be using 95.9. That's right. That's the doctorate mean. Do you see the master's mean was at 71.8 or something like that? That's right. Okay. So you see 95.9, 71.8. That's the means that you want to compare. Then I told you the S pool was 33 point. You told me actually. You copied it out. The S pool was 33.93. What goes inside the square root? 1 over what plus 1 over what, right? Again, this is just revision. There's nothing new here. We have done mean comparison CIs before. What do you need? I have conveniently pushed the screen to the right place. You're comparing doctorate and master, so do you get what I'm trying to say? All right. That's right. One of the sample sizes was 41, and the other one was, I think, doctorates had 41 people, and masters had 59. Good. Okay, the only thing to deal with is the multiplier. Let's go back to our slides. What's the rule? The multiplier, the rule says the multiplier comes from the T table. I hope you realize why it's a T table, right? It's a mean problem. T table. The DF is the denominator of S pool. If you remember, the denominator of S pool was add up all the group sizes less how many? 5. What was the total number of people? Does anyone remember that number? I think I told you to copy it down as well. How big is this data set? How many people were there totally in this entire data set? 243. Yeah. Good. So you should be using a DF. That was really good. It is 1.98. I'll tell you why. Okay. I'll explain here. The DF is 243 less 5. Okay. Which of course is unavailable. So you round down to, I think the closest was 120. This is where the 1.98 came from. Is this okay? Same story here, nothing new. You round down if what you need is not available. Okay, so now let's finish the slides. If we took the time to compute, I'm not going to ask you to write down the numbers. You just use decimals or whatever. We are 95% confident that the difference in the long run mean earnings of doctorate versus masters is somewhere between 10K and 37K or something like that. That's it. Again, I don't want to spend too much time on the interpretation because you have done this many times in the past already. We are 95% confident that the difference in the mean salaries of doctorates versus masters is between this and this. Okay. So while this screen is up, let me just ask you a few questions. You know where I'm going with this. When are you willing to generalize a result? If the original samples were, when are we willing to generalize anything in statistics? If the samples were random, good. And can we say that your qualification is causing you to earn more? Actually, okay, is there an association between your highest qualification and how much you earn? Yes. But can I say that your qualification is causing you to earn more or less? You cannot say that. Do you know why? Why can't you make a causation claim? Because this study is observational. What couldn't be randomly assigned? The degree. Yes, I'm so glad no one said you can't assign the salary. That is never a thing. Right? Good. So then you can generalize if the sample is random, but you cannot make a causation claim because you did not randomly assign people's qualification. Therefore, the study is not an experiment. Is this okay? Right? We're actually at the end of the slides. And that's actually it. Next class, we are going to finish group work on this and start chapter 10, which is the last chapter already. So I want us to practice this on a very similar data set once again. We don't have time to finish the whole thing today. I would ask you to do it as much as you can, then hold on to this for our next class. I won't collect it back. All right. We'll try to discuss some of it on Scratchpad before we go today. So let me just pass it out. So 1, 2, 4, 1, 2, 3, 4. And I'll of course show you where this data is. Okay. Okay. So where where is this data set? If you go to our class data page, you will find that there is a data set called, oops. Okay, use this one. Do you see Atkins versus other diets? The data is there. Atkins versus other diets. This tab. That's where the data is. So I want you to do all the things that you learned with me today. Okay. Anytime it says plot histograms, email your histograms to me as usual. Email a picture to me. Don't print it out or anything like that. Okay. Okay. So any questions with Jamovi, please raise your hand. All right, I'll help you out. Right, because it's new. But let's see how far you can go with this worksheet. All right. Don't worry about Scratchpad yet. I'm just doing this, setting it up. But after you're done, then we'll start filling it in. Okay, fill up your paper first. Try your answers on the paper first.
Maybe it's something that's like the long run. It's just like the long run. Yeah, the one. Is it yeah. Explanatory. That is protected by and then this one is yes. Oh, yeah. Because like there's like there's different diets, so I get it.
Yes.
You know March or
Oh, really? Okay, what was this scene exactly?
it just says that we just
Okay, that's because you're using the cloud one hands. Do you have it on your system?
No.
What machine are you using? Is it,
internet.
do you have is this a Chromebook or something?
It's an iPhone.
Oh, yeah. If it's a MacBook or not a Mac, then I think you cannot install it. You have to use just the cloud.
I got it. Just take it on that.
Yeah, first it's on now, but first it's still out. Yeah. It
Oh, yeah,
does work sometimes.
Oh, I have another question. So
Yeah.
if we go to this, like you said,
And over, that's right.
and then like this,
Yes.
like this, how do we see the like individual ones again?
Yeah, so that one you have to go to exploration, remember? If you want to see the pictures.
Oh, yeah.
Yeah, so that's right. Then you do the same. Right? Did your cloud wake up?
Yeah.
Yeah, it does that. That's why if you can, but if you don't have a system that has the ability to store the movie, then you have
What are
yes,
Oh, yeah.
yeah, yes, that's right. This kind of thing is like a big person. It doesn't. So, but what you can do is the top there, the big. Yes.
I have a question on the first about what the chi-square statistic is.
Yeah.
I just didn't remember what the assumption was.
No, you don't. Needs to move it from this.
Okay.
So,
Okay.
you really wanted to make this an equation, but.
Oh, no, I'd rather use it.
Yep.
For sure. Yeah.
Okay, so what you do is, it's a little bit more question of which of the data is formative. I recommend the research because yeah, I'm gonna list of them. Okay.
Oh, so, yeah, so, I just can't see you guys. Oh, wait, oh, yeah. I think that's like. Is that just like there's no effect for the characters between different there's 37 materials. Oh, you're technically, I already defined it, it's just like it's more because it was yeah, and then yeah, that's what that's and like the
Okay, maybe I can start asking some of you to fill in some of these things. Let's start with this one. Does anyone know what the explanatory variable is? Can you just type your answer here? That's right. I would say type of diet. Good. How many diets were there? How many levels? 4. Right. So now I would say BMI is involved in the response, definitely, but can we be a little bit more careful? What was the response? The word BMI is there, but did anyone catch that? Yes, it is the change in BMI. Very good. You know why that's important? Because if you didn't put the word change, does it make sense that, I mean, who has a negative BMI? No matter how thin you are, that's not going to happen. Okay? BMI doesn't work that way. So the fact that there are negative numbers means, and they told you, they recorded the change in BMI. Good. So the response is the change in BMI. Is it quantitative? Yes. Okay. I know we have not talked about observational units for a while, but I do want to check. Does anyone know what the answer is to this one? Observational units are not variables. I'll give you that much. Did anyone get what this is? It's just a one-word answer, actually. What were the observational units here? Yes, good. So why am I doing this? I'm doing this because I want you to differentiate. There are people who cannot differentiate between the variable and the unit. The unit is the thing that you measure the variable on. So don't conflate the two. The observational unit is the thing you measure the variable on. All right? To the people. So the people are the observational unit. You observe them and you measure the things on them. What is the research question? Anyone have a nice way of saying this? This is a non-jargony layperson way of describing the problem, basically. What did you hope to achieve in this study? Don't use the word mean and stuff like that. Right? Try to use non-statistical terms. A research question tries to be pretty. That's right. How do different diets affect the BMI? Something like that. Good. Very good. Okay. Did this study have random sampling? Just say yes or no. Yes. Good. And did this study have random assignment of diet? Yes. All right. So we had random assignment of diet as well. So can you answer that question? What does this tell you about how far you can take any conclusions that you come to? What are the implications of your answer with regard to the scope? When you say scope, it means how far can you take your conclusions? Anyone know the answer to this? The fact that you had a random sample means, yes, very good. You can make causation. In other words, if you find that one particular diet is associated with a greater change in BMI, you can say that diet caused it because there was random assignment of the diet. Very good. Generalization is because there was a random sample. Is this okay? Right? Okay, define what mu Atkins is. Anyone want to try this? Give me some words. Mu Atkins is the, not a number. Right? You cannot give me a number. This is a parameter. Mu Atkins is the long run. Mu is always a mean. Mean must always have a quantity of interest. Long run mean, again, the word BMI should be there, but we can be a little bit more careful. What about the BMI? It wasn't exactly BMI. It's the long run mean something BMI. What? This is linked to the research. Yes, I would say change in BMI. You know why? It's not that you're comparing two diets. It is an individual person's change in BMI. That was the response. So it's basically the response variable here. The long run mean change in BMI of individuals on the Atkins side. Very good. And of course, the others will be the same. Now, what is the null hypothesis? Can you give it to me in symbols first? The null says mu at, let's shorten it a little bit. Mu Atkins is what? The null says mu Atkins is equal to, what were the other diets? I think there's Zone, yeah, that's right. And then there's Ornish and Learn, I think. I think that's it. UL, that's right. What does the alternative say? We have not typed this out for a while. What does the alternative hypothesis say? Yes, not all mu's the same. Very good. Can you give the non-jargony one for the null using the language of association? Oops. There. Okay, can you finish the sentence? You need to learn how to tell the null hypothesis in a non-symbolic way as well. The null says that there is no, I use the language of association. There is no, that's right, because if you don't want to involve the word mean, you cannot say the word difference. There is no association between, that's right, between change in BMI and, very good. And of course, can you copy and paste and just modify one word for the alternative? The alternative says that The alternative just says that there is one. Good. Perfect. Okay. Use Jamovi to help with the following. Can I have someone do this for me? Don't paste a picture. Can I have someone paste the text of all those statistics here? You know what I mean? I believe the movie allows you to copy the text. It doesn't have to export as a picture. Can someone paste all the text for all the different means for the groups and all that? All right. Now, don't plot the histogram here. I want you to email those to me. So don't plot them here. But and we will end with C. I want to know whether anyone, by just looking at the histograms, did something jump out at you? You're not doing any statistical test yet. Just looking at the pictures that you made, the histograms that you made. Can someone, thank you, that's what I wanted. So you have all the statistics that you need. See the means and the, oops, I think this is not the right one. This is for the salary data. Sorry, can you do that again? And I believe this is unfortunately, I think, oh no, it's not a picture, good. But can you paste this again? This is for the salary data. I want it for the diet data, okay? Um, yes, thank you. All those 70 something, yes. These are for the diet data. See all the negative numbers? Good. And we will end with, okay, we will end with this. Describe what the graphs tell you about the diets. I am very interested to see what you have to say. And we will end with this, right? Don't paste Instagram, you email those to me. Anyone pick up anything from the pictures? Just what do the pictures tell you? Don't be afraid. Just tell me what do the pictures tell you? Just based off pictures alone, right? I'm interested to see if someone catches what I think is quite obvious from the pictures. Did you get that, right? Look at your histograms and see whether you get anything from it. All right. First of all, maybe answer the question, which diet appears anecdotally to be the best? Anyone get anything from the pictures? Just they are all, yeah, I agree. In other words, did you find that the diets don't seem to be very different? The tags for the diet can actually be interchanged. But if you really had to answer the question, which diet do you think is a little bit better than the rest? Did you get which one it was? Atkins, can you tell me why? Why did you say it is Atkins? Atkins looks a little bit better than the rest. There are yes, there were more negative values. Very good. And I'm guessing you know that the purpose of the diet is to lose weight or lose BMI. I mean, I know there are people who want to gain weight or whatever. There's diets for that, but mostly we want to lose BMI. So yes. Okay, thank you. So we will keep the papers, okay? Bring them for your next class and we will finish this class.